Greetings. We spent the first two lectures giving some introductory remarks about neural networks. In the first day, we talked about what neural networks did, gave a rough overview of neural networks, and on the second day, we talked a lot about some of the applications of neural networks. Okay, as we mentioned in the course, we said we're going to hit three topics: neural networks, fuzzy logic, and computational intelligence. We've touched on neural networks. We will return to it. I thought it would be fun to start off the course. It would be fun mostly for me because you have nothing else to compare it to. But I've always started out the course with neural networks and detailed discussion of neural networks. Thought we'd talk about it, lead off the course this time with a talk about fuzzy logic and the way that fuzzy logic works. Fuzzy logic has a long and interesting history. But it was culminated and actually advanced by a single paper, 1965, a paper by Zada. Dr. Zada is a professor in Berkeley, and he published a seminal paper, which is still available in reprints. Many times in a field you have a book, and in this book they have reprints of classic papers. Zada's paper has probably been referenced more than any other paper in the world. And with it, Zada presented a new paradigm. It's a different way of looking at the world. I remember that when I was a senior in college and I was just starting to understand about waves and electromagnetic waves and transmission lines and everything, I looked around and everywhere I looked was electromagnetic waves or waves. I even remembered when you had tissue paper on a roll, you pull and it broke off at the roll, and I thought, oh, of course, because it's a pulse down the paper and then there's an impedance mismatch at the roll, and because of this impedance mismatch, there's a break there. So anyway, a paradigm is a way to look at the world, and you learn different paradigms because it's a model. It's just a different way that you look at the world. Some of you had EE505 with me last quarter. Probability is a model, a way to look at the world. And when you begin to look around, you see, probability everywhere. You will see, if you understand the concept of fuzzy logic correctly, a paradigm in fuzzy logic. It is indeed a way to look at the world. Now, in the area of fuzzy logic in 1965, after Zada published his paper, there were a lot of problems associated with the acceptance of fuzzy logic. A lot because of the mindset of the people who were in, what do we call it, the cult of analyticity, as we talked about last time, such as Professor Bitmead, wherein they had a single hammer so everything looked like a nail, right? And that's the only tool you have. When a hammer is the only tool you have, everything looks like a nail. So it wasn't advanced for a long time, and unfortunately the word fuzzy logic was used for the name. I think the word fuzzy itself has had a negative impact on the acceptance of fuzzy logic. We were working about, I believe, 6 or 7 years ago with Boeing, and there was an engineer there that had developed a new fuzzy anti-skid device based on fuzzy control. And the Boeing anti-skid device that was under use at the time was somewhat mechanistic. It actually worked, but it failed at a certain places, so they tweaked it here, and it failed at another place, and they tweaked it here. It worked very, very well, but this anti-skid device worked also very well. In fact, much, much better and much more simple in terms of concept and design. But one of the problems which he encountered was one which you wouldn't expect. He got to the point where he told to sell it to management, and eventually got back the feedback, well, if you were a passenger, would you fly on anything that was designed using fuzzy logic? So the concept of fuzzy had a very negative connotation, unfortunately. Fuzzy logic was developed initially in Japan. It was discovered in the U.S. by Zada, who was an immigrant from Asia, but it was actually reduced to practice in Japan. And there are some people that argue that Asian philosophies are more interested and in tune with fuzzy logic. And we'll talk about that just a little bit, as opposed to Western philosophy, which is more of a Boolean sort of way of thinking. So with that, let's get into fuzzy logic. By the way, fuzzy logic has been reduced and is used in everything today, primarily in control. Everything from bullet trains to rice cookers to washing machines. It did some funny things. General Electric, when they first put out their American fuzzy washing machine, it didn't fit into the paradigm because you used to go into the washing machine place and they had these big yellow stickers on there that would tell you how much electricity it would use for a load at different settings. Well, with fuzzy logic, interestingly, there were sensors inside, and the fuzzy logic was able to adapt to the load, to the dirtiness of the load, to the type of laundry, to the load of laundry, and so it was an actually adaptive system. So therefore, you could put in exactly the same load, and it would take a different amount of electricity every time. So therefore, it took the entire concept of this governmentally imposed yellow stickers that you put on these machines and totally threw it away. So they had a difficult time in redoing it. So fuzzy logic is everywhere in much of the embedded software because it's really slick the way that it does work. As a paradigm, fuzzy logic has a very rich mathematical foundation. There are people that do things such as talk about fuzzy measure theory and talk about very deep axiomatic developments of measure theory based on fuzzy logic. There is axiomatic development of fuzzy logic exactly the way there is axiomatic development of probability. In probability, typically we start with 3 or 4 axioms or basic assumptions or basic truths, and from those truths build up the theory of probability. That same thing can be done from fuzzy logic. There are numerous journals which are totally devoted to fuzzy logic. Probably the most widely circulated is the IEEE Transactions on Fuzzy Systems. There is also the Journal of Approximate Reasoning, and there is there's another one that escapes me. But the Transactions on Fuzzy Systems is probably the most widespread. The interesting thing about fuzzy logic is the following. I used to say when I was introducing fuzzy logic that there are 2 areas in electrical engineering which are uniquely associated with a single individual. And by an area in electrical engineering, I mean an area in electrical engineering wherein within IEEE an entire society is developed, an entire journal has been developed, devoted to this topic, and there's annual meetings where hundreds and maybe thousands of people get together and talk about the topic. Now, one of those was fuzzy logic because it can be traced exactly to Zada's 1965 paper. And there used to be 2 people alive for which this was true. One was Zada. The other one died last year. Anybody know who that was? Yeah, you were in the course. Okay. Claude Shannon, who developed uniquely in his 1948 paper the entire field of information theory and did wonderful things. And the beautiful thing, Claude Shannon passed away last year, and because of Claude Shannon, the entire concept of information theory was birthed, and there's the IEEE Information Theory Society, there's the IEEE Transactions on Information Theory, and but he's no longer with us. A brilliant fellow. And just like Zada's paper, one of the beautiful things about these seminal papers, such as Zada's original 1965 paper, you can pick it up today and you can read it, and it reads intelligently. You can get insight and actually new ideas for research just reading this original paper, much like Shannon's original paper, just beautifully written, really, truly works of art. Okay, so let's look at fuzzy logic and see what we mean by fuzzy logic. Much like a blind man and an elephant. You've heard of the blind man and the elephant sort of story where blind men are asked to define the elephant, and one feels the leg and says, the elephant is like a tree, and the other one feels the side and says, no, an elephant looks like a wall, and the other one grabs his tail and said, no, the elephant is like a rope. Each one of them gives a different explanation, albeit an accurate description of fuzzy logic, just from a different point of view. Fuzzy logic can be viewed this way also, and I'm going to present you some different approaches to fuzzy logic and understanding fuzzy logic developed on the blind man and the elephant sort of way of doing things. One of the most important things is that fuzzy logic attempts to accurately model inaccuracy. You might say, well, doesn't probability try to measure inaccuracy also? Yes, it does, but it's a different type of inaccuracy, as we will see. Richard Feynman, most people know who Richard Feynman is, don't you? He was the guy, I think he made his appearance to the American public primarily after the Challenger blew up, the space shuttle blew up, and he was on the investigatory panel, and everybody was arguing back and forth, no, it's this person's fault, it's this person's fault. And he took out some of the material that the O-ring was made out of, and he says, look, I found out that if I take this O-ring and I dip it in, and he did this right in front of everybody, and I dip it in my glass of ice water. He was in this panel where you had your pitchers of water. He says, look what happens when I take out. It's brittle. And from that simple explanation, he was able to actually zero in the fault of the explosion to the O-rings. Very brilliant man, winner of a Nobel Prize. Also kind of wacky. He left his job and nobody knew where he went, and they found him somewhat later in his life playing bongos in a beatnik club. So he's a very interesting fellow. Anyway, he said when using a mathematical model, careful attention must be given to the uncertainties of the model. And certainly that is true. Many times we get the theory and the reality mixed up, and the uncertainties of the models are very, very, very important. This leads to Mr. Spock's folly, that precision is not truth. If you watch some of the early Star Treks, Kirk comes on and says, we'll be there in 3 days. And Spock comes up and says, 3.6259 days to be accurate, Captain, which is really ridiculous, because once he gets to that fifth decimal place, the time that it took him to say that sentence is longer than the accuracy of that fifth decimal place, so it really has nothing to do with the accuracy, right? So that's what we refer to as Mr. Spock's folly. And fuzzy logic is an attempt to model this uncertainty. I don't know if you can see here at the bottom. I learned something in putting together this lecture. You know what XTMPRSZNTWLFD is? That's a word. Anybody know what that is? No Trekkies in here, huh? That's Mr. Spock's first name. Ooh, okay. One of the things that's going to be confusing, I think, when initially confronted with fuzzy logic is the difference between fuzziness and probability, fuzzy logic and probability. Here is probably a good place to talk about probability, and we'll talk more about probability and fuzzy logic. But probability itself can be fuzzy or crisp. Crisp is the conventional way of doing things. Boolean algebra is crisp. It's either 1 or 0. We'll find out that fuzzy logic takes the 1 and 0 and smears it out into all sorts of different possibility. Well, there's actually fuzzy versus crisp probability. When we study 505, we talk about crisp probabilities. The probability that a fair die will show a 6 is 1/6. That is, we roll a die, the probability that it's a 6 is equal to 1/6. Everybody would agree on that. That is a number which is precise, although it's a probabilistic measure. Do you agree with that? So all credible mathematicians will agree on this exact number. However, if you go to channel 5, 4, and 7 and you listen to the weatherman's forecast of the probability of precipitation tomorrow, you'll find out everybody has a different estimate of that probability, don't they? Some will say, well, we have a 90% chance of precipitation tomorrow. Some will say we have 92%, 85%. And all of these are calling this probability of precipitation a probability. And it is kind of a probability because they made an educated guess on the current state of the what is going on. But nevertheless, it is not a crisp probability. It's a fuzzy probability. So here is an example that indeed illustrates the probability itself can be crisp and fuzzy. Probability can be certain or it can be uncertain. There was a forerunner of fuzzy logic called Lukasevich logic, which is the logic of half-truths. Lukaszewicz looked at original Western logic, and he looked at the classic Boolean logic, and he said, okay, let's take the possible Boolean variables, and let's look at the different operations that we have. We have the operation of, what is that, intersection and union. Intersection, of course, being same thing as multiply, that being and. And so if we go with the intersection, we all know that we get 0, 0, 0, and 1, whereas with the union, we get 0, 1, 1, and 1. And then there is also the inference, like A infers B. Well, if A is false and B is false, what does A infer B? It's almost like it's exactly an exclusive OR, by the way. Well, in fact, let me just put that up there, an exclusive OR. An exclusive OR, we get a, no, it isn't. It's the opposite of the exclusive OR, isn't it? It's the exclusive NOR. Because 0 implying 0 is 1. False implying truth is 0, 0, and 1. So we have these classic Boolean sort of operations. Lukaszewicz came along. I hope I'm saying his name right. Lukaszewicz came along, and he says, suppose that you had things which were half true. Now, what can be half true? We'll talk about half truths. In fact, a fundamental big faux pas in Western philosophy on half truths. And he says, suppose that you not only had a 0 and a 1, but you had a half also. So let's have something which is intermediate, and he came up with Lukaszewicz logic. And see if you can help me on this, because I think once you see it, you go, okay, yeah, that makes sense. Okay, here's the problem. Instead of having 2 Boolean variables, now we have 3. We have a 0, a 1, and a half. And what is a half? Well, that's kind of a half-truth, right? So here's A and B, and these are the possible the possible combinations for Lukaszewicz logic. See, did I get everything? By the way, you spell his name Lukaszewicz, logic. And by the way, this is L3, meaning that we have 3 levels of truth. We have 3 levels of truth. We have false, we have true, and then we have intermediate. I think you can also see that Lukaszewicz would say, we have an L4 sort of logic where we have a 0, we have a third, 2/3, and a 1. So we could divide up the logic into as many different partitions as we can. Lukaszewicz was actually ahead of his time, because as we'll see, Lukaszewicz logic, when carried to the limit, when we actually have an infinite number of possibilities of truth. That is, there's a sliding scale between 0 and 1, all intermediate values. This corresponds to fuzzy logic. So this is kind of a partition which eventually is going to lead to fuzzy logic. Well, let's take the operations. Let's take the AND operation. We know everything with the Booleans already. Okay, we know what that is. Now, what if you had a statement, compound sentence, saying Jane is here and Frank is there, okay? And you assign truth to it, and Jane was not here and Frank was, I don't know, half the way there. Would that compound sentence itself be true, false, or a half-truth? It'd be false, wouldn't it? Because the first part was false. Just logically, it makes sense, right? So indeed, this would be 1/2. And you might suspect that this is a half here because it does turn out to have a commutative sort of property. What about a sentence connected by an and where the first part was a half-truth and the second part was a half-truth? What would the overall truth of the sentence be? Just intuitively. It'd be half-true, right? Because the first part was half-true, the second part was half-true, so the whole thing is half-true. So this turns out to be a half. And then finally down here, if you have a sentence which is connected by an and the first part is true and the second part is half true, what about the entire sentence? It kind of takes on its weakest value, doesn't it? It takes on the value of a half. The entire sentence for a and or an and operation always kind of takes on its weakest value. You'll notice that a 0 and a 1 gives a 0, 1 and a 0 gives a 0, and a 0, 0 gives a 0, and a 1, 1 gives a 1. In each case, the value of the conjunction is equal to the weakest link, if you will, in the logic. And indeed, we see that here also. So 1 and a half also turns out to be 1 half.
But that's not true for your 0 and 1 half.
The 0, oh, you're right, you're right. You're right, and I'm sorry about that. You're right. So if the first one is false, no wonder you were looking at me with crooked eyes. Okay, yeah, if the first one is false and the second one is half true, then the entire statement is false because this one muddies the water for the entire statement to be totally false. Right? So I'm sorry, I misspoke on that. Let's do it with the union. Now the union, interestingly, does what? It takes on the strongest value in general, doesn't it? If we look at the Boolean case, we had to get a 0, we get a 1, we get a 1 here, and we get a 1 down here. So in each case where we have this Boolean statement, we have the strongest variable taking on the dominance in the the union operation. So let's see if that logically makes sense. If you say this is true or this is true, the first statement is false. The second one is half true. You have a or in the middle. What about the composite sentence? It would be half true. It takes on the strongest of the two components, doesn't it? And indeed, that's what it does elsewhere. It takes on the value here, and then down here, what about if the first one is true and or we have an or and the first portion is true, the second portion is half true. The whole concept would be true if it was connected by an or. Is that right? So in each case, it takes on the strongest value. So this is Lukasevich logic, and Lukasevich logic can take on 3 levels, 4 levels, and 5 levels. You might ask, what is an example of a case where you had logic of this sort? Well, actually, when we get into fuzzy logic, it'll become very, very clear where these came from. But I think classically, one justification, as we see from the bottom here of the slide, is so-called bipolar paradoxes. And in a book by Bart Kosko of USC, in discussing fuzzy logic, the entire concept of fuzzy logic is introduced by bipolar paradoxes. Kosko trying to make a case that Boolean is a Western sort of phenomenon, and whereas Lukasevich and fuzzy logic is more of an Eastern sort of concept, which you'll see. One of the places where bipolar paradoxes come into enormous play is in Gödel's proof. How many have heard of Gödel? Okay, 2 peep 3. Okay, a fascinating history. And in fact, in Time Magazine's list of the 100 persons of the century, the following 20, I think, no, there's more than 20. The following are the most influential scientists and thinkers of the 20th century. And one of them is Kurt Gödel. And I think I'm saying that right. Any Germans in here? A G-O umlaut is G. Okay. Yeah. So I was trying to fancy up my name, which is Bob, with an umlaut. Because that looks cooler, right? Except it's pronounced bib. Is that right? Huh? Bib?
It's I can't even. Like Goethe or
Bed.
it's something that doesn't sound correct.
Okay. So I have. There was, I believe, in the Clinton administration, there was for Attorney General Zoe Baird, and she put an umlaut over her name. She wasn't even German, but it kind of looked cool. Okay, so I wanted to do it, but not. Can't have deep. Doesn't work out. Okay, so Kurt Gödel, who was a mathematician, who totally rocked the world of mathematics with a application of a bipolar paradox. And a bipolar paradox is actually a failure of Boolean logic, which we'll show you. You might have heard of some of these concepts, but there's some interesting things from Gödel's proof in so-called meta-language statements. A meta-language statement is a string of words which refers to itself. There's actually a feedback loop that goes in there. So meta-language is language that refers to itself. For example, this sentence contains 5 words. That's a sentence that refers to itself, right? So this is referred to as meta-language. It's true. So meta-language can either be true or false. You can assign it values of truth. If we had this sentence contains 6 words, well, that's a false statement. That's a false statement. So there are certain meta-language statements where we can talk about one being true and one being false. There's the paradox of the liar, which is usually attributed to Epimenides from the 6th century BD, who was a Cretan, who got up to speak and he said, all Cretans are liars. This is actually meta-language if you take into account that the speaker is a Cretan. And when he comes up and he says all Cretans are liars, he's referring to himself. All of a sudden, you're put in a paradox, because if they're liars, if he always tells a lie, then he just told you a lie. Which means all Cretans aren't liars, right? But if all Cretans aren't liars, well, then where does that leave you? Do you see how it goes back and forth? And the reason we refer to it as a bipolar paradox, because it's almost like a flip-flop. Your logic and interpretation of that concept go from one area to the other one. Now, many times we see these things and we think, they're kind of funny, but they actually have a deepness, a philosophical deepness in our Boolean interpretation to the world. Here's some other meta-language paradoxes, very similar to the Cretans' liar. What I am telling you now is a lie. I'm telling you a lie right now. You see? If I'm telling you a lie, well, then what I said is false. I'm really telling you the truth. But if I told you the truth and I'm lying to you, well, yeah, but if I lied to you, I'm telling you the truth. And so you go flip-flop, 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 back in your Boolean logic, back and forth and back and forth and back and forth. Here's another one. If this sentence is true, the next sentence is false. The previous sentence is true. This is also a bipolar paradox. You can go through this and you can go, okay, if this sentence is true, the next sentence is false. Okay, well, let's see. Well, the previous sentence is true. Well, if this previous sentence is true, then this is false. Well, if this is false, then this is true. And you flip-flop back and forth in terms of the logic. It's very interesting. I minister only to those who do not minister to themselves. Then the question is, who ministers to me? Okay. I minister to only those who do not minister to themselves. Then who ministers me? If I minister to me, well, and that violates my assumption. I only minister to those who don't minister to themselves. Well, I minister to myself, so I can't minister to me. But if I minister to me, I can't. Nothing is impossible. This is a theological argument. Can God make a rock so large you can't move it? It's a bipolar paradox, born of Western logic, because it flip-flops back and forth in your head. Everything is possible. Well, if everything is possible, name something impossible. Right? Everything is possible. Well, if everything's possible, then name something that's impossible. That's something. Bipolar paradox. Then there was Russell's paradox, which he actually came up with in 1901, where actually Professor Danborg talks about this Russell's paradox in his EE 510 class. Any of you had the EE 510 class? Okay, did he talk about Russell's paradox in there? You don't remember it. Okay. I know that one time Professor Danborg was teaching the class, and I was watching it on Channel 27, and he came up with the Russell's paradox. This is the paradox of this. You have two types of sets that contain themselves and sets that don't contain themselves. Yeah, normal sets and what, abnormal sets? And then the question is the set of all abnormal sets normal or not? Well, it turns out by doing that you go into a bipolar paradox, because your mind flip-flops back between the two concepts. And so all of this fun stuff, which is kind of like parlor tricks in terms of messing with your logic, actually took on a very, very serious implication in some of Russell's work. Okay, here's Gödel's proof. He was, by the way, at Einstein, with Einstein at Princeton, or when Einstein was there, came over from Europe. Gödel's proof looked at the axiomatic development of mathematics. Hopefully you're familiar with the concept of Euclid and his axioms or his postulates, on which were built the entire concept of Euclidean geometry. The axioms were self-evident things that were true. They were just assumptions. They were either self-evident reality or assumptions that you made. And from these axioms or postulates, one was able to develop a very nice complex math. Euclid had how many postulates? I don't remember. I think 3 or 4. In the probabilistic course that we teach in EE 505, we don't go through the axiomatic development, but we do refer to the axioms, and there's 3 axioms for probability. And from these axioms, mathematicians, and this is not a mathematics class, it's an engineering class, but mathematicians can take these 3 postulates and the concept of logic and develop from that the theory of probability. What Gödel showed in the 20s is that all such theories are either incomplete or inconsistent. Remarkable, very, very strange result. In other words, Gödel was able to show that any axioms that you had, that once you began to develop them, that they would either be inconsistent. Let's see, do I have a definition of one inconsistent? They would either be inconsistent in the sense that you could show contradictions. If they were inconsistent, you could show that 1 + 1 is equal to 2 and 1 + 1 is not equal to 2. So you could show something and the exact opposite of it. That's what inconsistent means. Or incomplete, meaning that there's something that you can't prove. And you might think you can go back to your axioms and maybe add an axiom to it in order to maybe take care of that one. Well, if you do, there's going to be something else pop up. Gödel's original proof was very complicated, and I don't pretend to understand it. I have read more lay interpretations of it. But it boils down to basically a bipolar paradox as applied to mathematics. In any system, the basic premise is you can state a theorem, which we will call Theorem X, which says Theorem X cannot be proved. Gödel's proof, I'm sure, is more fundamentally aesthetic than this, but this is what my understanding of what it boils down to. Theorem X cannot be proved. Well, what if you can't prove Theorem X? Then it's incomplete theory, right? Because there's something you can't prove. If you can't prove Theorem X, there's something you can't prove. It's an incomplete theory. On the other hand, if you can prove it, then it's inconsistent, right? So therefore, this bipolar paradox, basically with Gödel's magic touch, and he did it much more formally than we're doing here, was able to totally topple all attempts to develop all arithmetic and math from some fundamental axioms, which at the time was being attempted. So again, if we can prove Theorem X, then the theory is inconsistent, because proving Theorem X is inconsistent with Theorem X. On the other hand, if we cannot prove theorem X, the theory is incomplete. That is, there are things we cannot prove. So Gödel's proof basically said that all theory logically developed from an axiomatic foundation is ultimately either incomplete or inconsistent. Now, Costco makes a point that in the foundation of all axiomatic development, we ascribe Boolean algebra, or Boolean sort of concepts, to the proofs that we take these axioms, that we apply to these axioms to build corollaries and lemmas and theorems. There's a Boolean sort of concept. A implies B, B implies C. And if A is true, then B is true. Or sometimes we do proofs by contradiction, right? Which is the contrapositive. B bar implies A bar, etc. So there's a Boolean foundation in all of the things. And in fact, there are some who ascribe this to our Western beliefs. Let's see. And here's a couple of quotes which are kind of, I thought, kind of applicable. This is from Hamlet. There is more in this world than you have dreamt of, and all your philosophies are ratio. Do you realize if Gödel is true, and none of this, do you realize how profound that is? That's really amazing, that no axiomatic development can do everything. There's also a quote from the Bible. It says, "For now we see through a glass darkly, but face to face, now I know in part, but then I shall know, even as also I am known." So the concept is that no matter how smart we are, no matter what we do, we're always going to have this dark glass that we're looking at, and there are things which are unknowable, according to Gödel. There are things which are unknowable. Now, the question is such logic more compatible with Asian philosophy, which I don't pretend to understand, but I'll try to convey to you what I have been told. I have been told that in some Asian philosophy, it is not that bad a thing to hold two contradictory concepts simultaneously and not be bothered by it. Indeed, this is something that we have a very difficult problem with. And indeed, fuzzy logic, Lukasevich logic, attempts to do that, attempts to look at different levels of truth. We are so embroiled in Boolean ways of thinking of things, it's amazing. And it's actually kind of stupid in certain cases. You're drunk in the state of Washington if you have what? 0.08% blood alcohol, right? So 0.079999, that's okay. Okay, 0.8, just that little bit more, then you're drunk. That's kind of a stupid definition of drunk. The concept of drunk is a gradually increasing thing. All of our justice is based on Boolean logic. Guilty, not guilty, 1 or 0. Yeah, really, if you think about it, just like with drunk driving, there's various stages of guilt, isn't there? Yet we are so embroiled in logic that we need to take this gradient of possibilities and apply to this gradient of possibilities a threshold, call everything on one side 1 and everything on the other side 0. And we do it because it's simple, but it always doesn't make sense. So this is one concept and one introduction into the concept of fuzzy logic, and has been actually said by some to be the reason that fuzzy technology had to be developed in Japan instead of the United States, because they had a philosophy which could understand it better. I don't know how much truth that is, but nevertheless, it's an interesting proposition. So I give it to you for your consideration, and you decide whether it's true or not. We said there was different ways of looking at logic. One was the uncertainty. The second was this concept of half-truths and the failure of Boolean logic, as illustrated by Gödel's proof, for example. The third one is as a contrasting measure of uncertainty to probability. When you're introduced to fuzzy logic, your initial reaction, if you're typical, like me, is saying, this is just a very strangely described version of probability. And it isn't. It's a totally different way of thinking about things. So I want to spend a little bit of time telling you the difference between probability and fuzzy logic. Fuzzy logic is said sometimes to refer to and to talk about the concept of possibility as opposed to probability. Possibility versus probability. If you went to the thesaurus and looked up probability, you'd probably have possibility there, wouldn't you, right? But if you think about it, there are some actual significant differences. Let's go over some of those differences. And both of them, by the way, refer to future events, don't they? When we talk about probability, we talk about a future event. When we talk about possibility, we talk about a future event. But they actually mean different things. Probability measures the probability. Possibility is measured by fuzzy logic. All things probable are possible. Is that true? It's probable that this lecture will end today, right? Is it possible it'll end today? Sure. If it's possible, if it's probable, it's possible. But the converse is not true. All things possible are not probable. This lecture could go on for 4 more days. It could, right? There's a possibility. But what's the probability of that happening? Very small, right? So, this illustrates very interestingly the difference between probable events and possible events. All things probable are possible, and all things possible are not probable. And then we have the contrapositive. Remember, with contrapositive, you have A implies B, and then you switch the B and the A and put complements over the both of them. That's the contrapositive. If the forward statement is true, the contrapositive is also true. The contrapositive of the two statements on the top was, impossible events are improbable. Let's see, is that true? If something is impossible, is it improbable? You betcha. Right? If something is something absolutely cannot happen. It's impossible. It cannot happen. Then is it a very small chance it'll happen? Of course it is. But improbable events are not impossible. Okay, so those are the contrapositives of the two statements. And if you think about these a little bit, you can begin to understand and distinguish the difference between probability and fuzzy logic measurements of uncertainty. Engineering for possible events is different than engineering for probable events. Say, for example, you were in the ocean looking for a submarine, and you wanted to develop an algorithm to put out your spies to search for that submarine. Well, there's a couple of ways you could do it. You could look at all possible places that submarine would be, right? Or you could look in probable places where the submarine would be. And if you looked in probable places, you would just be looking in places where, you thought it would be, and it would be a totally different engineering task than to looking at all possible cases, correct? So possibility versus probability enters into engineering design in what we do. Which one's more difficult and more costly? Looking at all possible cases, right? Because that means we've got to look everywhere. Here's another interpretation. Blind man and the elephant. Here's another interpretation of fuzzy logic. Is that fuzzy logic has the ability to take fuzzy linguistic variables and reduce them to a mathematics. We many times convey information to each other in fuzzy concepts that are not very precise. I would say, man, that guy was tall. That is an imprecise description of the person. It's a characteristic. And I have an idea in my mind what is tall, and you do too, and we're able to communicate using that fuzzy linguistic variable even though we haven't precisely defined what tall is. If the car was going very fast, that's a fuzzy linguistic variable. We have an idea what fast is between us, yet we haven't precisely defined it. In classical control, if I was telling you to back up a truck, and I was using conventional crisp control, that is very precise control, I would say, back up your truck 6.32 feet. And that's what you would do. But that's not the way we tell people to back up a truck. We say, come on back, slow down more, more, slower, slower, stop. In no case there did we convey anything of precision. They were all fuzzy linguistic variables that we were able to control that truck by, even though we weren't very precise in doing it. And that's the way humans communicate. One of the nice things about fuzzy logic is it takes these fuzzy linguistic variables and offers us a mechanism, and this is exactly what fuzzy control is, as we'll see. Offers us a mechanism by taking these concepts and putting them into software, putting them into an algorithm. And fuzzy logic is basically what was based on exactly the way that we would do things. When a cook says add a dash of salt, it doesn't say exactly how much salt, it's a dash. I don't know what that is. That's how much you can pick up with a pinch, right? A dash of salt. And so if one were to develop a recipe that way, one could actually use fuzzy logic to take a recipe with all of these inexact rules and develop it into an algorithm. So this is another interpretation of fuzzy logic. And in fact, it's one of the most powerful ones, I believe, because it's a very nice impedance match of the way that we think and the way that we communicate to computers, because it allows an interpretation, what's that when you go from one language to another? A translator or something, a compiler, I don't know. It's able to take what you are thinking in the manner that a human is thinking, even an expert, and develop software which does, or an algorithm which does exactly the same thing. And the example of fuzzy and crisp control is a very good one, because we do tell people to back up and do things using fuzzy linguistic variables as opposed to conventional crisp sort of ways of doing things. So here's an example of a fuzzy linguistic variable. The term far I have no idea what that first sentence means. Okay, I'm going to have to take this out. These slides, by the way, are available on the web. Okay, here's examples of other fuzzy linguistic variables. Close, heavy, light, big, small, smart, fast, slow, hot, cold, tall, short. They all correspond to a measurement of something. Now, many times we can talk about these sorts of things, and many times we can quantify things. We can quantify close. How would we quantify close? By distance, right? It would be something we could measure. Heavy by weightage, light by poundage, smart. How would you categorize smart? By IQ? I don't know. Fast. Yeah, that would be velocity. Hot and cold by temperature, tall and short. There are things whichever you can't measure exactly. You might say somebody's really ugly. Okay, that's a fuzzy linguistic variable. Man, that person's ugly. And how do you quantify that? There is no measure, there is no sensor, there is no artificial, things you can pick out of air which measures ugly. What you have to do in such cases where things aren't measurable is do what we do all the time. They said on the scale of 1 to 10, that ugly is a 8, okay? And in fact, that is what we refer to as assigning a fuzzy membership. You know when somebody does a dive and all those judges put up all of the cards? Those are just like those fuzzy probabilities that the weatherman is doing. They're trying to establish on a scale of 1 to 10 the degree of the goodness of that dive. Same thing with skating, right? Because you can't measure the precision that you would in some of the other sports such as baseball and football where everything is supposed to be crisp and mathematical. So diving and ice skating are fuzzy sports. Baseball and football, ideally, if you take away the errors of the referees, are crisp sports because they're supposed to be totally defined by the geometry and the mathematics of what's going on. Okay? And assigning these numbers is said to be assigning a fuzzy membership value to the event. And notice that this fuzzy membership function can be assigned to not only things you can measure. Close. Well, how close was he? I don't know, on a scale of 1 to 10, how close were they? About a 3. Okay. You can actually use fuzzy memberships to do close, even though you can define close in terms of distance. You could also measure close in terms of this on a scale of 1 to 10. But you can also do it with things that are not, I think ordinal is the word, things which numbers cannot be assigned to, such as ugly, or how good a dive was, or something like that. So, on a scale of 1 to 10, how good was the dive? The difference is in fuzzy logic, we don't put things on a scale of 1 to 10. We choose a number between 0 and 1, where 1 is totally true and 0 is totally false, and everything in between is a gradient difference. And you can see that Lukasevich logic is a special case of that. Instead of dividing it into a scale of 1 to 10, they said, okay, we're just going to have 3 scales. On a scale of 3, 0, 1 half, and 1. So that would be Lukasevich logic, L3 logic. Here's another example that fuzzy is not equal to probability. I'm sorry. Okay. Billy has 10 toes. The probability Billy has 9 toes is 0. The fuzzy membership of Billy in the set of people with 9 toes, however, is non-zero. Let me explain what I mean. In conventional Boolean logic, when you talk about sets, you're either in the set or you're out of the set, right? It's one or the other. You're in the set, you're out of the set. You're either 1 or a 0. With fuzzy logic, you are into 1 degree or another into the set. We can talk about the set of tall men and the membership function, which we will denote by mu here, of tall people. And tall is a fuzzy linguistic variable, right? Now, suppose that I had up here Andre the Giant. How many know who Andre the Giant is? How do you know him? From Princess Bride, right? The movie. Let's see if we have any WWF fans here. Okay, 8 foot. I would agree, I hope we would all agree, somebody that's 8 foot tall in the set of tall people is 100%. I mean, that's tall, right? So it's 100%. What about a guy that's 6 inches tall? Where would that person be in the set of tall people? 0, right? What about somebody that was 5 foot 6 inches? I don't know. This is one of the interesting things about fuzzy logic. When we ascribe these membership functions, we know that this membership function probably goes up like this, and that we would all agree that the boundary points, that 8 foot would be 1 and that 6 inches would be 0, and we kind of figure out that the taller you are, the more you are in the set. But you and I might have in our minds a different membership function, and yet we're still able to communicate. This is one of the beauties of fuzzy logic, that we don't have to have the same membership function. We just have to have basically the same shape. And we'll talk about the robustness of fuzzy logic to the shape as we go along in the class. What is that? What about 6 foot? 5'6". I say it's about a third. I don't know. 6 foot would be about a 0.8. Oh, it's my opinion, right? It's my opinion. But I tell you what, when I say tall, and we're trying to communicate, your idea of tall better be kind of close to my idea of tall, or we're not going to be able to talk to each other, right? So we basically all have these fuzzy membership functions in the back of our minds. Now, what about crisp sets? A crisp set for the height of somebody would be the set of people over 6 foot tall. You're either in the set or you're out of the set. A membership function in that case would be 0. Anything below 6 feet would be 0. You'd be out of the set. Everything above 6 feet would be in the set. So it turns out that all conventional crisp membership functions look like this. They're step functions, if you will.
What do you think Andre the Giant's concept of tall?
It might be different, but I think the guy thinks he's tall. Okay, you know, he knows that he's tall. So when people first see this concept of a membership function, they say, this is the same thing as the probability of being tall, because it kind of has the flavor of a cumulative distribution function, doesn't it? has that flavor. And there's a confusion going in there, and that's the reason we spent time discussing the difference between possibility and probability, and leads us back to the same slide. Let me go over this slide again now that you have this background of a membership function, okay? Billy has 10 toes. Can you see my marker? No, you can't see none. Oh, it's terrible. Okay. Okay, Billy has 10 toes. The probability Billy has 9 toes is 0, right? If he has 10 toes, what's the probability he has 9 toes? 0. But if you were to look at the membership function of people with 9 toes, okay, here would be the toes, number of toes. Well, if you got 9 toes, you're 100% in the set, aren't you? Right? We should say here the fuzzy membership in the set of people with close to 9 toes, because we need a fuzzy linguistic variable there. Close is the key word here. So this is the mu of close to 9 toes. Okay, well, you're totally in the set here. What if you have 10 toes? Well, you almost have 9 toes, right? No, seriously, you almost have 9 toes. So the membership function for the people with 9 toes might look like this, okay? So the membership of Billy, I guess you have 9.5 toes. You can also have fraction toes here. Billy, who has 10 toes, has a membership, say, of 0.3, according to this graph, according to this membership function, in the set of people with close to 9 toes, right? Yet the concept that he has, the probability he has 9 toes is equal to 0. So again, difference between the fuzzy membership function and the probability statement. You don't know how long I had to look on the web to get these pictures. This is a guy with 11 toes. I forget where I found them, but it was... Okay, you can look at those at your leisure. Here's another one which was given by Jim Bezdek. Jim Bezdek was the founding editor of the IEEE Transactions on Fuzzy Systems. And the first issue, he put out a very nice introductory paper which gave the history of fuzzy systems. He talked about the difference between probability and possibility. And this is one of the examples he gave, which I think was really good. You're in the desert. You need water. And you find a bottle. And you pick up a bottle and you read on it a half. And you wonder if that's possibility or a fuzzy membership function. It makes all the difference in the world. If we are talking about contents of, say, sewer water, if it said on there that the probability that this contains sewer water was 1/2, as opposed to clear water, potable water, what would you think? Hey, there's a 50-50 chance you could drink that, right? But what if it was in the fuzzy membership of liquids that had sewer water in it? In the second case, we are guaranteed it has sewer water in it, right? Maybe about half sewer water. So in fuzzy membership terms, this thing has half sewer water if it's a fuzzy membership. If it's a probability having sewer water as opposed to clear water, then you got a 50-50 chance that this is clear, drinkable, potable water, right? So this might make a determination on whether you drink it or not, or even open it. If it's the membership function, you probably wouldn't even open it if you know that it's half sewer water in terms of the membership. But if it only has a probability of a half of being sewer water, you might take it open and take a sniff to see whether you could drink that or not. Okay? So here is, I think, a very beautiful example defining or illustrating a difference between fuzzy membership and probability. Okay, we have about 10 minutes left to talk about some other fun things as we go into the concept of fuzzy logic operations. Thus far, we have only talked about these things from a conceptual point of view, And now we want to talk about the formalism, the precise modeling of uncertainty. It almost sounds like a bipolar paradox, but it is not. The precise modeling of inaccuracies in terms of fuzzy logic. How do we characterize it? Well, the first thing we do is recognize that we are generalizing the concept of conventional crisp sets. Crisp sets means 1 and 0, Boolean. If we have a Boolean sort of system, that is a crisp system. An element either belongs to the set or it doesn't belong to the sets. Fuzzy sets, on the other hand, have grades of membership, as we talked about here, with people with close to 9 toes and the membership of people in this set of tall people. So fuzzy sets have grades of membership. We might talk about the fuzzy linguistic variable far. And this is an example of a discrete fuzzy measure. We have a set, the set of cities far from Los Angeles. On a scale of 1 to 10 or 0 to 1, we're actually doing 0 to 1, the membership of cities far from Los Angeles, we are going to include in our domain Los Angeles, Chicago, New York, and London. On the set of cities far, well, Los Angeles cannot be far. That has a membership of 0. Because you don't have to go at all. Los Angeles is not far from Los Angeles. Chicago, that's a little bit closer. We'll give that a membership of 0.5. Notice the heuristics that go into the assignment of these membership functions. They are very heuristic. 0.8 to New York and 0.9 to London, because clearly Chicago is closer to LA, New York is closer to LA, and London is closer to LA. So we can either have, in terms of membership functions, the continuous type that we have here, or we can have a discrete type as we have here when our domain is discrete. Here's continuous fuzzy membership functions. We might talk about a fuzzy set B of numbers near to 2. This is kind of like when you get near to 9 toes. Well, we're not sure what it should be, but we do know that it should be kind of a single bump curve kind of centered at 2, right? If we talk about things near to 2. So let's call it 1 over x minus 2 squared. That gives us a nice bumpy thing that maximizes out at 1 close to 2. Is that right? No, I don't like that. I got to change that. That goes to infinity, doesn't it? Oh, that's bad. Forget that one. Forget that one. Here's a nice one. E to the minus x minus 2, which is a Laplacian curve, which is kind of centered at 2, right? The point that I want to make here is that the membership function of things which are near to 2 is not unique. It is fuzzy, and there is uncertainty about the assignment of the membership function. It's just that we have an idea of what the general shape is. With conventional sets, we have the concept of being a subset or not a subset. And one of the things that we'll do as we talk about this is see if the definitions of fuzzy sets match what we refer to as a boundary condition. When we make a proposition for a fuzzy rule, such as a fuzzy and or a fuzzy or, we need to look at that definition and see what happens to that definition when we apply it to not general fuzzy sets, but to actual crisp sets. And when we apply it to general crisp sets, it should boil down to the Boolean operation with which we are familiar. So that's what we mean by a boundary condition. And we'll see a boundary condition here. We see a fuzzy set A is said to be a subset of B if the membership function is less than the membership function of the other one. So here A is a subset of B if their membership functions are smaller. So in other words, what we're saying is the following. Suppose that we had the set of, say, tall people. We said it might look like this, which went from 0 to 1. So this is the membership of tall people, which we'll call mu sub A. Should not we have the set of very small people be more restrictive than this? Shouldn't the set of very tall people be a subset of the set of tall people? Just intuitively. Yeah, the set of very tall people should be a subset of tall people. So let's say B is very tall. Well, let's go up here to James Arness. Played Matt Dillon on Gunsmoke. He was 6'7". Right here, he's about 0.9 in the set of tall men. What about in the set of very tall men? Should that number be less or greater than 0.9? Should be less, right? Because very tall is more restrictive. So for very tall, it should be here. And indeed, shouldn't that be true for every point that we have? Because very tall is much more restrictive than tall. And so what we will have for the membership function of very tall is a mu sub b here, corresponding to something which is very tall. And you can see that in order for this to be true, u sub b must be less than or equal to mu sub a, which is a requirement for being a subset. Makes a lot of sense, yeah.
Would the shape of the curve change as well?
The shape of the curve could change. But again, the choice of the curve is actually heuristic. Many times very tall, e.g. means, for example, mu sub b can sometimes be equal to mu sub a squared. This is a common operation which you use for vary, when you apply vary to your fuzzy linguistic variable, because mu sub a lies between 0 and 1, so if you square it, you're always going to get a number less. This doesn't have to be the way that you do subsethood, but it is a possibility. Okay? Now, let's look at the boundary condition. We all know what a subset is in terms of crisp Boolean logic. The question we need to address in each of these cases is if we look at this definition for fuzzy logic and fuzzy sets and we're to apply it to a Boolean set, will this operation take on exactly the same form in the Boolean set as we're used to? Now, if you have a Boolean set, let's take, for example, the set of C is a crisp set of people greater than 6 foot tall. So C is going to have a membership function which looks like this, where this is height. You can choose, well, it'd be 6 foot, right? Now let's look at another one. Let's look at D, which is the set of people over 5 foot tall. Yeah, that's fine. Which one of these is the subset of the other one? Yeah, C is contained in D, right, is a subset of. Now, this being the case, this is our conventional understanding of crisp logic. Does this apply here? Is indeed mu sub C, I'm sorry, mu sub D, no, let's see, mu sub C less than or equal to mu sub D. Do I have that right? Yes. Answer is yes. Right? So therefore, by using this as a fuzzy element of subsethood, we have passed the litmus test that when we go to conventional Boolean logic, that the concept of conventional subsethood still holds. I've illustrated it here. We could go into more detail, but I think you can see indeed that's the case. Okay? So what we will do next time is, don't go yet, we will go into similar operations for complement, anding, and oring. We'll explore things such as De Morgan's law and other Boolean sorts of concepts. We will propose in each case a fuzzy operation to operate on fuzzy sets which perform this operation. These were proposed by Zada in his original 1965 paper. We will illustrate that they meet an intuitive condition and also meet the boundary conditions that when we apply them to conventional crisp sets, that they do indeed apply. Any questions at all? Okay, we will see you then on Thursday. Thanks for your time.